Okay, so ion implantation is a very important process, and we have seen this or briefly discussed in the context of making SOI wafers, right? You implant a lot of hydrogen for a smart cut process, or implant a lot of oxygen for the CMOS process. If you remember, SOI wafers, okay? And we will have a slightly more detailed look at this process. So, it's very important. In fact, you've heard about the transistor scaling, right? Transistor scaling. You did not learn this in the device course? Yeah? Next lecture. Okay, good. So, we are on time. So, the paper that described the scaling theory was titled Design of Ion Implanted MOSFETs. Ion implanted MOSFETs with very small physical dimensions. Okay. So the paper that described the scaling theory actually had ion implantation as the enabling process, explicitly mentioned in the title. Okay. So that is very important. So that actually tells you what is the importance of this for small dimension devices. So what we have seen, a couple of, meaning two different ways of introducing impurities or dopants into silicon. One was during the crystal growth, right? You melt silicon, you can add whatever you want into the solution, right? And then make a mixture and then grow the crystal. Okay, so then the grown crystal will be doped. And the other was to diffuse. Yeah? So we have seen the diffusion process. But these things are, diffusion, these are high temperature processes, by the way, right? Crystal growth. Crystal growth means the entire wafer will be one type of dope. Diffusion, I can use this to selectively dope regions by using some diffusion masks. Okay. But this is a high temperature process, 900 degrees centigrade, 1000 degrees centigrade, and so on. So I need actually masks which can withstand these temperatures. Okay. And in VLSI processing, this is not very good because we have seen that if I have an N-channel MOSFET and a P-channel MOSFET, one place you get boron, another place you have arsenic. Boron diffuses much faster than arsenic, and so on and so forth. So I don't want to do a lot of high temperature processing, right? Just enough to get all these things in place with low defect density. Okay. But if I'm going to do a diffusion, then I have a problem. So I'm looking for a much lower temperature way to introduce dopants into silicon. Okay. So the ion implantation is a perfect thing, and there are very important aspects here, like I can use a mask, okay, which can be photoresist, so it doesn't have to withstand very high temperature process. Okay, so I don't have to intentionally heat the wafer during the ion implantation process. Okay, because I'm actually just going to implant accelerated ions into silicon. Okay, so when we have seen this, right, when we discuss the plasma processes, right, depending on the energy of the incoming particles, different things can happen, and one of that is that it actually gets implanted into a material. So that is one thing. So you can use photoresist as a mask for implantation. Okay, low temp, because it is you don't have to intentionally heat the wafer, but the wafer may get heated during the implantation process. Okay, so that we have to see. Okay. Okay, so now the other thing is that you are implanting ions. So I can connect this in an electric circuit and measure the ion flow. Okay, so if I am implanting ions, and this is the only way of flowing current in that circuit, okay, then I can actually measure the current and integrate it over the time of implantation. I get the total dose. How much did I divide it by the ion charge of the ion, right? That gives me how many ions are actually implanted in. Okay, so I can very easily measure the dose by just measuring the current, implant current. Okay, so which also means that I can precisely control the dose, total dose that is implanted. But we can't control what has gone where. Meaning, what has gone is definitely, but where. So that is something that we'll see in a moment. So there comes a little bit of complexity. And then there are some difficulties though. So you use ions which are accelerated to 2 kV, okay, 1 kV and so on, or half a kV, 200 kilo, meaning 0.2 kV, so 200 electron volts and so on are low energies. You can go to mega electron volts of acceleration also, meaning kinetic energy. Okay. Now, how much energy do I need to break silicon-silicon bond? Okay. So this is in the range of, and create a displacement. Okay. So knock off a silicon atom from its lattice side. So this is about 15 electrons. 15 electrons. So even for the lowest energies that you use for ion implantation, you can actually knock off multiple atoms from the lattice side, creating vacancy in the stitchal pair. Okay, so which means that when you do the ion implantation, you inevitably create damage in your crystal lattice. Okay, so this is not a good thing. Which means that the ion implantation has to be always followed with an annealing, a thermal treatment to bring these things back, remove the defect. Okay, so that is not bad because after the ion implantation, I don't need the photoresist or mask. I remove the mask and do the thermal annealing. Okay, so this is a very important thing. So the dopants which are introduced can actually diffuse. Okay, so first thing is they actually can redistribute and go back and sit at this lattice side. Okay, so there can be a lattice reconstruction, right? But also they can diffuse. Okay, so these are two important things. So the annealing process should be targeted to completely eliminate the defects. Okay, so that is very important. But in VLSI, you also would like to reduce the extent of diffusion during the annealing process. Okay, because we don't want deep junctions in your VLSI. You know, source drain junctions, extensions for example, have to be like 1/3 of the gate length. Okay, if they diffuse too much, then I would not be able to have controlled shallow junctions in the device. Okay, so this is very important. And the ion implanter is okay. So now there are problems. Ion implantation is actually, it's using an ion beam, a very narrow ion beam, but you have a big wafer, right? So it actually goes by raster scan. Okay, I'm scanning it like this. Okay, so by definition or by implication, this would be a slow process. Okay, so this is not a high throughput process. Okay, very good control, and you can do it at low temperature, very good things, but the throughput is not very high. Okay, and typically this ion implanters also break down often. So I've listened to one of the presentations from Infineon Technologies. Yeah, they make this power semiconductor chips, smart power devices, and so on and so forth. These days, in the olden times, they used to also make DRAMs. I think they still make. Okay. So one presentation from an engineer, production manufacturing person from there. He said, in terms of the tool breakdown, ion implanter is the most frequently breaking down tool in the whole manufacturing. Okay. So this means it's quite expensive heavy instrument. So you would not find many university labs which have iron implants. But you can make something, a little bit of a small system using what is called plasma immersion iron implantation. Okay, but the capabilities of the tool would be much limited compared to a beamline implantation. Now, another thing in a beamline implanter is that you are actually taking an electron, or meaning ion beam. Okay, so I can accelerate it, so I can actually easily change the kinetic energy, right? And also I can tilt the beam by applying electric and magnetic. Okay, so I can have directionality, right? I can have it coming vertically down, beam that is coming vertically down, but I may also tilt it. Okay, so I can also get it tilted. Okay, because I can steer it using electric and magnetic. Okay, so these are things that you don't have in your diffusion process. Yeah, this is very important. We'll see that later. Okay, good in certain aspects. Okay, not so good in certain other aspects. But this is actually widely used, and in fact, one of the important specification of an ion implantation process is the tilt angle. Okay. So you may do two things, the beam can be tilted or the wafer can be tilted. Yeah? But in diffusion it does not matter. You will diffuse wherever there is a concentration gradient. Okay, we'll discuss it in more detail in the next lecture. Okay, yesterday we started the discussion of ion implantation, right? So today we'll continue that. So as I mentioned, ion implantation is the preferred process for doping for VLSI manufacturing, and the main advantages are that you can easily mask this, right, using photoresist, because you don't have to high temperature process for introducing the dopants into the silicon in this case. So that gives a big advantage, and also you can precisely control the total amount of ions introduced or dopants introduced into the center. Please switch off your mobile phones. So if you now look at ion implantation, how do I actually study this? Okay, so this is one software you can actually see this shrimp, which is very widely used for ion implantation of ions into amorphous materials. Okay. This is used not just for VLSI kind of thing, but any ion implantation processes that we explore. Shrimp is actually very widely used. So the expansion is the stopping and ion range of ions in matter, and this is actually originally developed by some scientists from IBM. And what it does is Monte Carlo simulation of a ion trajectory. Okay. So what is Monte Carlo simulation? Have you heard about Monte Carlo?
Large number of particles where the particles can have variations and movement according to some random values.
Yeah. Okay, so but then you are talking about particle simulation, but general thing about Monte Carlo. So what is Monte Carlo? This is not. It's not. The meaning of Monte Carlo is not casino. Yeah. So this is. There's a small country called Monaco. Okay. This is between France and Italy, somewhere in the corner down there. In Europe, so it's one of the principalities of Monaco. Okay, so if you go there, and there is one gambling place. Okay, it's one of the most famous gambling places. Some palace do something is the name of it. You can go there, of course, and also enter this place. Yeah, and see it from outside. Not if you want to go inside, then a lot of other things. So I've gone there once to see this place. So now gambling is very risky business. Okay. So this is basically used for. So it's something like it's a chance. Yeah. So in gambling, it is about chance. Yeah. So it's if you say that okay, I will win, or let's say two players are actually playing, one of them have to win, right? Okay. But if the chances are equal, right? For example, the gambling house. I'm running a gambling house. Okay. And then 100 people are coming and playing against the house, essentially, right? Yeah. So there is something. If the chances are equal, then I'd make no profit. So there's something called house advantage in gambling, where I will always profit. Yeah? This can be in different ways. Okay. But of course, Monte Carlo but this is used. It's not Monte Carlo. I mean, they have given this name to a methodology for statistical simulations. Okay. So if I take this example, I want to implant this ion. So what is uncertain about this process? So you can think of a crystal and then ions are implanted. Okay. So ions have high energy. So what is uncertain about it? What is probabilistic? Yeah, so basically, the ions are going in and actually they see this atoms arranged inside this solid. Now, will they move in a straight line? No. Okay. So they will interact with the particles inside this metal, inside the solid. Okay. And it can interact with the particles in different ways. Okay. So there is something called nuclear interaction, which means that your ion is positively charged. It goes and actually is meeting a silicon atom, right? So the nuclei of these two would actually repel because they are positive charges. So there is the nuclear interactions, which leads to nuclear stopping. Okay? So some energy may be transferred to the silicon atom in this case. Okay? The other thing is you can have, the outside this core of the atom, the nucleus, you have the electrons. So the electrons of the two, once it is inside, it gets neutralized, but it still has some. Okay, so it has some charge, but in some time it will actually get neutralized. Okay, but then the electrons of this implanted species can interact with the electrons from the atoms. Okay, so that can then deflect the atoms because they will repel, right? So that is one thing. So in that process they can lose some energy. Okay? So this is called electronic stop. Yeah? The other is actually a Coulombic stopping of a different kind. So where you have a positively charged ion entering this material, okay, and you can think of this material as, let's say, a lot of electrons, yeah, in the material. So this goes in with positive charge, and the electrons will then start to surround this because it has negative positive charge. Okay. So then they would actually now it is not this ion that is moving, but also the electrons may actually move along this. So then it's a larger number of charged particles, right? Moving towards. So it actually then slow down the ions. Okay. So this is the other electronic stopping process. Now, in which direction this would, if I have an interaction between two nuclei, okay, as a consequence of this, how will the incoming ion deflect? Can I decide this very precisely? Okay. So this is actually a very difficult problem, because you may be able to do this if I exactly know, for example, it's a head-on collision, right? Yeah, head-on collision. But on the other hand, if it is coming like this, right, moving, there's a, so I don't know. Yeah? So this is there's one very interesting book called This Chancy World, okay, which is basically a very in popular science. This is popular science talks about probability. What is right? This Chancy. So this would then. So you don't know how the ions will be scattered around, right? How they lose energy. So what is done in a Monte Carlo simulation is each of these interactions are treated as a probabilistic event. Okay. So some probabilities will be assigned to each of these interactions, probability distribution, and then you are in SHRIM. What they do is you will shoot ions one by one. Okay. So what you see here is, for example, this ion. So you can actually trace just one line starting. So you are actually implanting. So this is your, this is the depth. Okay. This is the surface, and you are doing the implantation at this point 0. Okay. And all the ions are implanted here. This is the way it has been simulated. So implant all these ions enter here, but they are actually scattered randomly, and they end up in different places. Okay. So you can trace this. So this ion has actually come up to this point and stopped, and this one has gone further deep. Yeah. This is because it has gone through multiple scattering events, and they have been deflected. So now you can also do this. You can download this program and it runs on Windows. So you can see this. Actually, it takes a lot of time because if I just do one ion implantation, right, I will not be able to actually say what is the average distance the ions would actually be implanted. Okay. So what you then need to do is to do a simulation for a large number of ions, and this example is for boron, 100 kilodecaloids. Okay. Okay, so this is usually what we do is this, right? But we'll just see the unimplanted. So we'll look at some examples from MOSFETs and so on. This one is showing the full slide. Okay. So some part is missing here. So you can see here, this is a schematic of an ion implantation system. Yeah. So what you see here is an ion source. Okay. So you have you then accelerate it to low voltages. Okay. So the whole thing is in a vacuum. So you have vacuum pump, and then there is a magnet which is used for steering the ions. Okay. Now what is the purpose of this? So when you do this, when you have the ion source, it may give you singly charged ion, doubly charged ion, and so on. Okay. Or maybe there can be some impurity also. Because you build this ion source with materials other than what you want to implant. Okay. So you may have something from the material which is used for constructing this ion source. Okay. So if I take, for example, arsenic, singly charged ion and doubly charged ion, and I'm going to accelerate this by applying some voltage. Okay. So If it is doubly charged, then the acceleration would be larger because the mass is the same, but the charge is twice compared to a singly charged ion. Okay. So if I apply a voltage of, let's say, 200 kilovolts, and a singly charged ion would be accelerated to, or will have actually a kinetic energy of 200 kilo electron volts, but doubly charged would actually have 400 kilo electron volts. So as a consequence, the higher energy ions would actually go deeper into the target material, into the substrate where you want to implant. Okay, so that is a very important consideration. So you want to avoid this kind of scenario. It's not just that you want to, eliminate ions of other elements, but also you don't want differently charged ions of the dopant you want to introduce. Okay. So what is being done here is, this is a magnetic sector. So essentially you apply a magnetic field, right? So it will deflect the ions, and what would be the force on the ions? What would be the force on ions? So you can actually write this. This is the force, so you can write this as Q into V cross B. Okay. So this is a magnetic field, this is a velocity. So that you can calculate from the energy which you use for accelerating the ions here. So the radius would be fixed, right, by the magnetic sector, and then you can steer these ions, and the radius will depend on the charge. If it is doubly charged, right, it will actually not go through this segment. Okay, so you have an aperture that is used to filter this, so other ions may go like this, right, or bend more. Okay, so this is used for actually removing those unwanted ions from the implantation process. Okay, then you apply this acceleration, right? This is where you are applying. So when you say that I'm doing a 100 kV implantation, right? An implantation. This is what the acceleration mentioned. Okay. Now, when you do this acceleration, meaning during this transport, some of these ions can get neutralized. That is possible, right? But before the neutralization, let's say they have been accelerated. Okay. So neutralization happens after the acceleration. So you don't want to actually get them here, so that I want to steer this beam around. Okay. So I don't want this the neutral species to get into the system, because it will just go and hit the wafer somewhere. Okay. So I would actually use, this is what is called a neutral beam gate. Essentially you apply an electric field to deflect the beam, and only ionized ions would be deflected. A neutral species will not be deflected by an electric field. Okay. So that is the idea here. And then, so this is what is called a neutral trap, and then you have your wafer is here, right? This is your wafer, okay? And you have what is called a Faraday cage to actually, this is a chuck on which you place the wafer, and it is connected through an arrangement like this, so that you can measure the charge. This is essentially an integrator, right? Integrates the current that goes into the capacitor, and that gives you the dose. Okay, so that is the basic schematic of the ion implantation. Okay. So you can find out the Q, the dose by this equation. Q is the charge of the ions, and A is the area or which the implantation has been done, and then I is the current. Now, very important thing is that, see, you have to, this is your wafer, right? It can be quite big. So, but the implantation is done using a very narrow beam, okay? So it would actually be, the doping will happen only locally. Okay? I need to now scan the beam. Okay? So I can do one of two things, or both of it. So I can move the wafer, or I can deflect the beam by using electrodes. Okay? Now, the fact that the ions are actually coming they're accelerated in a certain direction. Okay, so that is a very important consideration when you are using ion implantation for making devices. Okay, so this is, if I am actually implanting on a planar surface, I can do an implantation this way. Or do you think there will be a difference if this is a wafer and I implant along a line, or along line which is perpendicular to the surface, and I actually tilt the implant? Will there be any difference? This is a point, right? It's a point.
Instead of going deep, it will go in certain direction.
Yeah, so of course, if I look at the vertical depth from the surface, since it is being, so you need to actually know, if it is going to get implanted 100 nanometers, it will be 100 nanometers this way. Right? You need to calculate the depth. But there are some other okay. So we'll discuss those things. Now another point is this, that since it's a kind of raster scan kind of process, okay, the throughput is actually not very high, so I can't use this for making solar cells. Meaning I can, people have actually demonstrated high efficiency solar cells using ion implantation, but the throughput is not very high, and as a consequence, I would not be able to use this in solar cell manufacturing, because there the cost is very important. Okay. Then there are some other factors like impurity getting that you get with phosphorus diffusion, okay, from POCl crystals. So that is not, we will not discuss it here. But I think I already mentioned about gettering. Okay, so this is, now it's very important to construct what is called a profile. Okay, so it is very clear that the ions would not sit at well-defined. This is what you are actually implanting a very large number of ions, right? Very large number of ions. Okay, so it is possible for us to talk about distribution of the ions, right? And then what is the average depth? Okay, and what is the spread of this distribution? Okay. So what you see here, again, STEM simulations of 99,999 ions of boron implanted into silicon at 100 kiloelectron volts. Of course, this takes a lot of time. Yeah? If you're doing the simulation on your PC, you will have to wait a couple of minutes to complete the simulation, because it's actually implanting one by one the ions. You can see the ions. Now this is at the end of it, it shows on the screen the implantation. Okay, so this is where you have implanted, right? Introduce the ions, they get scattered in all directions, and you get components. Okay, so this is the way that you actually have a plane and or a substrate here, and you're shooting ions like this. So this image is you're looking from this side. Okay? But this one is you're looking from this side. This is your plane into which you're implanting. So you're looking from the, or maybe from this side. So it actually also goes deep, but also laterally. Okay? Okay. So you can now look at what is the distribution for this. So that is a very important thing, as I mentioned, the Monte Carlo simulation, it will take a lot of time. Okay, but it's actually useful in certain cases to study this. Do Monte Carlo simulations, because if I have a large device, okay, let's say a 1 micron channeling device. Okay, so let's say I have 1 micron length, 1 micron width, and 1 micron deep. Let's say half micron deep junctions. Meaning, or actually the channel region, so it's, let's say depletion region is half a micron. Okay, to make it simpler, we'll assume this is 1 micron. Okay, so you're talking about 1 micron, cubic micron, right? So this would be how many cubic centimeter? 10 raised to minus 12. 10 raised to minus 12. So cubic centimeter, right? So this is 1 micron, cubic micron is nothing but 10 raised to minus 12 centimeter cube. Okay, but then suppose I have in the doping here is what? 10 raised to 17. Okay, per centimeter cube. Okay, so how many dopant atoms will be in the device depletion region? Just multiply, right? So 10 raised to 5. Okay, 10 raised to 5. Fairly large. Okay, but now if I take this device, 1 micron, right, and then scale it to 10 nanometers, what happens? So 1 by 100, right? So that becomes 10 raised to minus 18 per centimeter cube, right? 10 nanometers. So this is the volume. Okay. 10 nanometer width, 10 nanometer length, 10 nanometer depletion region width. So of course, I need to dope it higher, but you can see that if I have the same doping concentration, right, in the channel, on the average, you can always talk about a doping of 10 raised to 17. But if this is the volume, I don't know whether there is a dopant atom in the channel. You get the point, right? So let us say I would actually, okay, so let's not go to such dramatically. So I would increase the doping 10 raised to 18 per centimeter cube. Maybe it is needed to control the short channel effects or whatever. So what does it mean? In this channel of the MOSFET, you may have one dopant atom, period. One dopant atom. It may be there or may not be there. Okay. So then it becomes important to do this kind of simulation. Yeah. So the averaging does not work when your devices are really very small. Okay, so you can see this thing has been studied quite extensively. So this is actually called variability, device variability. Anything about very small devices, you need to worry about variability. So this is one thing. So if I'm making an extremely small MOSFET, okay, so dopant fluctuations. First of all, the number of dopants in the channel source drain are not the same for every device. Okay. As a consequence, the characteristics of these devices would vary. Okay. Lot more than an 1 micron technology device. Yeah. Because you are talking about a dopant being there or not. There is nothing else, right? You can't say that half a dopant is there. That's not possible. So this is a problem. Yeah. So this is meaning this is a very dramatic example, but I think it conveys the message. Okay. So this is one source of variability. Then there are other sources. For example, if you are defining a gate, okay, the roughness on the edges of the gate. Yeah. So locally the channel lengths are not the same throughout the device. Okay. So if I have this is my active region, right, and this is the gate. Okay. So I actually draw this a little bit. Some random. Okay. So the gate length is not identical everywhere. So if the gate length is smaller in some region, the leakage current increases, usually exponentially. Okay. So then and the threshold voltage would be different at different places because of short channel effects. So you have a problem. This is another problem, right? So dopant distribution. So variability is a very fundamental issue in very small devices. Okay. Okay, this is a slide where what I have done is the boron this time implanted with a 10 kV, 10 kilovolt acceleration, same number of ions. So you get the profile, okay, from the shim. Okay, so the profile is taken at which location? Point where you introduce the ions, right? So you are actually looking at this place, this location, 0 that I mentioned on a previous slide. Okay, injected ions at this point, and then they spread down. You are actually taking a cut along this. So that gives you the distribution of the dopants after the implant. So 10 kV is the energy in this case. So I can, this can be fitted using a Gaussian program. So the line is actually the dots are the dot points, and then the line is fit of this Gaussian function. Okay. So I can talk about what is called the projected range. So RP is the projected range. So that is this, right? This is the mean of the distribution. Okay. And then there's something called straggle, and standard deviation. That is delta R. Okay. Now, so you can, this is your Gaussian distribution. I can characterize this. I know the dose, so I integrate this, right? I should get the dose. Okay. So if I integrate it, I get this number, and I can find out from summations on these parameters. Yes. This one. So what I have done is that you have seen the implanted ion distribution in the previous slide, right? And that was actually you can do this count of ions, okay, at each location. So I'm drawing a line through this 0, right? So a line that is horizontal to this axis, okay, along the point 0, because that is where you introduce the dopants. Okay, so you can then, so you get the count, and then you can translate it to the concentration per unit volume, and that's what is plotted here. Okay. So in this particular example, the range, projected range is 48 nanometers. Straggle, that is the standard deviation, is 20 nanometers. Okay, about this. But you can also see that it has a lateral distribution as well, about the same line. Okay. So that would be then, that is called the lateral straggle. Lateral straggle. Okay. Now this is interesting thing, and lateral straggle is important when I do a mask implant. So if I take a substrate, right? So this is the surface. Okay. I'm introducing the ions, right? Here. Okay. But in fact, I'm not just shooting one ion at a time. I'm actually using a beam. So each of them would actually create a distribution. Right? So they will overlap and so on. And then I scan the beam around. So this is my beam. I just scan it on the way. So you can see this distribution will overlap. Right? Then you have to add them up to find the broken distribution on the wafer, and if you have done it well with slow scanning and so on, you will get same distribution, vertical distribution everywhere. Okay. But suppose I now put a mask here. Okay. This is an oxide mask. Yeah. Oxide mask. Okay. So here the profiles will be something, right? You have, if I draw a junction, right? Let's say this is my junction. And but here the implant will go into the oxide, right? Assuming that gets implanted to the same depth. So there is nothing in this part of the silicon. Or is there some detail that they miss? Yeah, so they were actually here at the edge. The lateral straggle becoming. Okay. So the ions would actually spread from this side, right? Or to lateral. So I would have something. So the junction would look like this. So that is why, if you remember, whenever we drew the MOSFET, right? The junction was shown like this, right? Even though this is the edge where you are implanting, it will always shown like this. Okay? Because this gate was the mask for the implant. Right? So now this triangle is important for, lateral straggle is important for scaling of the MOSFET, because you don't want this is my, what is my gate length? Is this the gate length? This is a gate length, right? But what is important for scaling is what? Channel length. And this is my metallurgical channel length. Okay, that's small. And this decides the short channel effects. Okay? Junction. So I can't have lot of, this is my gate length defined by lithography and etch processes, but if I have lot of straggle, then I have problem. Okay? Because I will not be able to make a very short device. So this is, these are some data thoughts from the book by Plummer. And what do you find here? The energy, implantation energy. Okay, this graph is implantation energy, and then the depth. Depth is nothing but the vector range from the previous slide. Okay, so if you look at this, right, you can. What is the conclusion? For the same energy. Okay, so these are common under use of silicon technology. So arsenic is heavy, right? Antimony is also heavy, right? And then you have phosphorus, boron. So this is the lightest of them all. So the same acceleration voltage, actually, boron will go deeper, much deeper. Okay. So let us say I want a depth, meaning the projected range of 50 nanometers. Okay. So for making, so I have a requirement to make 50 nanometer beep. Okay. Not the junction, but it would be, let's say, the peak of this profile would be 50 nanometers. Yeah. And then I would want to make both N-channel MOSFETs and P-channel MOSFETs. Right? So if I do make an N-channel MOSFET, I'm going to implant either arsenic or phosphorus. Okay? For P-channel, it should be boron. So what would be the energy required for phosphorus? Meaning, let's say boron, what would be the energy required for phosphorus? What would be the energy required for arsenic? From this graph? Yeah, so boron approximately maybe 10-8 or something, right? Phosphorus, that would be about 30 maybe. Arsenic, it would be 70, 75. Okay, you see the difference. Okay, now what about the straggle? So this is the not the lateral straggle, vertical straggle. So that also changes with the energy. Okay, so lighter the element, it actually gets scattered. So that is very easy to understand, right? It does not get scattered. You can't easily move a heavy iron around, right? By scattering, you get reflected, but it does not move very far. Okay. The lighter element would actually not lose much energy. Now the challenge for VLSI is the following. So if I take this 8 kV acceleration for boron and then 75 for arsenic, right? And I should get the same depth. Okay. But then, what is my problem? Subsequent to this, I need to anneal, because I am going to create damage in the silicon, and the dopant atoms are sitting somewhere. Okay. For them to contribute to conductivity, I should get them to the lattice sites. Okay. So I need to anneal this damage, okay, reconstruct the crystal, yeah, and the dopants should occupy lattice sites. Okay. So this is called dopant activation. Yeah. You bring them to lattice sites, so that is called dopant activation. So you do high temperature anneal, which will do both this. You are removing the damage by reconstructing the lattice. Okay. So when I do this, the boron being lighter actually diffuses much faster than arsenic. Okay. So even if you got a the same profile for boron and arsenic by using two different energies, yeah, after annealing, the p-type junction will be deeper because boron is diffused much more than the arsenic. Okay. So I need to then design my implantation taking that into account. Right? I should actually bring this to smaller values, still smaller values, because after annealing, it actually can go deeper than arsenic. Okay? So this is what I mentioned. Always you need to worry about what you're going to do. What any process is going to do on things that are already on the wafer, right? So if I am doing a high temperature process, I should keep in mind that all these dopants which are implanted, of course that will not be a constant value, right? The doping concentration. It would have a profile, and as a consequence there will be diffusion. Okay? So I need to worry about diffusion when I am doing any high temperature process. Okay, this is now very important thing that we talked about for implantation. It is easy to mask the implant. Okay, so if I look at this, so I have the mask here and then silicon. So that can be this region. Okay, the device, right? Implanted this. So we are looking at the sliver here, right? That. So the implanted ions, most of them end up in the mask, okay? And some may get into the silicon, okay? If the thickness of the mask is not large enough, okay? So this is an important consideration. Now you can see that I would actually, just take this profile. So you can do some calculations here. So if I assume that the mask, only mask is there and it is very thick, okay, then you would have an implanted profile which should look like this, right? Yeah, the continuation of the Gaussian function beyond this point, right? If it was only mask, okay, there is no silicon, okay. So what you are saying is, okay, so you might have got some of this thing actually has got distributed into the silicon, okay. So that can be used for getting some basic idea about what would be the total dose that is implanted into the silicon. So essentially you take this Gaussian and you integrate the doping concentration from this point, okay. This is called the thickness of the mask. So if it is 0, so this is xm, okay. So xm to positive infinity. If you integrate the Gaussian profile, you get how much dopants have gone into your silicon. Okay. So that is what you are doing. Why is this important in a MOSFET or any thing? For let's say I take gate, okay, and then a transistor, and I want to do this source drain implant, right? So the gate is actually acting as the mask. There is no other mask, okay, for this process. So if the gate is thin, what is the problem? Let's say I am going to implant boron here, okay. So boron gets implanted here as well. If it is thin, yeah, what would happen? Okay. So see, it doesn't have to be very thin, because this is usually the concentration of boron in the source drain would be in the range of 10 raised to 20 per centimeter cube. Okay. But here you would have N-type dopants because of P-channel transistor, and the doping concentration will be in the range of 10 raised to 17 to 10 raised to 18. So 2 to 3 orders of magnitude smaller. Okay. So the residual, the tail of this profile that gets into the silicon, with this of this boron implant, okay. So you are talking about a P concentration of 10 raised to 20, and then tail that is 10 raised to 17, for example, right? Then you already have a problem, because this would be either arsenic or phosphorus, okay, N-type silicon, and a little bit of boron is getting into this. So what would be the net concentration, doping concentration? Nd minus Na. Okay. So Nd is the donor concentration, Na is the acceptor concentration. Right? This would be the net doping. Okay, so as a consequence, the net N-type doping concentration, net electron concentration in the channel region would actually come down. Okay, so you can now see the problems with this. Your short channel effects will increase, for example. Doping concentration is decreasing, so short channel effect. This is not. Yes. No, see, you need, so if I have a very thick mask, everything will be inside the mask. Right? So you can see it here. Okay. So this is my profile. I'm talking about 3 orders of magnitude difference, right? So this is 2 into 10 raised to 18, right? And I'm talking about 2 into 10 raised to 15. So the mask should be thicker than this. Okay. About 125 nanometers. Yeah, 125 nanometers. Yeah. So this is the line that you're talking about, right? We'll come to some value. If the mask, so I'm talking about how to design a mask for an implantation. Okay. If it is very thin, I have this problem, this kind of problem. Which shape? Oh yeah, so so there is something called stopping power of ions in the material into which you are implanting things, right? Ions. So the stopping power would depend on how heavy the element, the atom is. Both, yeah. But let's say I am implanting boron into photoresist and silicon. So usually silicon being heavier than carbon, right? Meaning it is usually organic. So you would have a slightly higher stopping power in silicon than in photoresist. Okay. So it depends on what you are. So if I'm doing an implant through metal, for example, right? So usually if I take, for example, gold, usually you don't use gold, but it's heavy, much heavy compared to silicon. So the iron stopping power of gold will be more than that of silicon. So it depends. So this is just to capture this difference in the stopping power, because we talked about 2 different types of stopping mechanisms. One is the nuclear stopping, right? The other is electronic. Electronic, we have 2 types. Okay. So these 2 materials may just have 2 different stopping powers. So that is why. Otherwise, if they had the same stopping power, it would have just continued the same shape, right? It just would have continued. Okay. So typically in silicon technology you use photoresist, but also sometimes whatever is there on the wafer, for example, polysilicon, silicon oxide, silicon nitride is a common material on the wafer when you do implantation. So these are the common masking materials. Okay. Okay, so this was what I was actually talking about, right? You have the source drain implant, okay? And during that process, you may have this kind of compensation and consequence, the change in the short channel effects, threshold voltage, and so on. Okay, so I can do an analysis, very simple analysis. So you take this profile, and all the important things are marked on this profile. Okay, so you're trying to find out what is the concentration of the dopant, okay, at this point xm. Yeah. So that is the thickness of the mask. Okay. So you know the profile, right? This is your Gaussian profile in the masking material. Okay. And you are assuming that the profile shape would not change. Okay. But it is not strictly correct because okay, here it may not change, but in this part it could change. There is some process called recoil. So if you implant something onto a material, it may bounce back. Some of these ions may bounce back. Right? This is a recoil event. So it might happen that you have, if this is a heavier material, right? You may have a slightly higher concentration around this, okay, inside this masking material, because of the recoil. But we are assuming that is not the case. And this is your Gaussian profile. You actually substitute this xm in the equation, and the concentration that you get. Okay. So if I am talking about this MOSFET, it should be less than the concentration of the N-type dopants in this example. That's what we want to do. Okay. Or any doping concentration, you are saying that the implanted species concentration should be less than a certain number. Okay. In a MOSFET and a p-channel MOSFET, where you have a polysilicon mask, it would be something like this. Okay, the CB will be something like this. Okay, and the range here would be the stopping mechanisms would be identical in this case, right? Because this polycrystalline silicon, this crystalline silicon, so same material, right? Yeah. So this analysis would easily apply. So I just want to find out what should be the, what energy I should use, this, right? So you can then rewrite the equation in this form. Okay. So you essentially are writing this in terms of, so xm is here, right? So you're basically rearranging this equation. Okay. And then you can find out the dose in that region. So that is this, right? This is the QP, okay? And you find out the dose by integrating this distribution from xm to infinity. Okay, is that it? So this will be an error function Gaussian profile. So it will be an error function you need to use the tables to find the values. So you can then calculate two things. What should be the dose, right? And also look at the tables to find out what is the RP corresponding to a particular energy. Okay. Then based on that you can decide what is the energy that you can actually keep these numbers within the, meaning the xm can be decided based on this. Okay. So you can find the CB from this equation, or actually the RP and delta RP combination can be determined from that. Because you need the tables, some information about the implantation. Okay. You can't just analytically solve this. You need to have the information about the range and the stagger as a function of the electron, meaning the acceleration energy. Okay, another thing is that you are implanting ions with very high energy, okay, and the ions are stopped inside the material. Okay. So ions have kinetic energy, right? When you stop these ions, what would happen to the energy? They'll actually heat up the substrate. Okay, so you can actually then determine what is the deposited energy, okay, on the substrate, so that it will be integral of the, this is the energy density per unit area, right? So the acceleration voltage multiplied by the implant current, okay, density, and integrated over time. So you get the energy that should be dissipated. So you can calculate, this is the acceleration voltage, Q is the charge of the ion, right? And the capital Q is the dose, okay? Because the acceleration voltage is constant, which is known as, you usually implant the constant acceleration. So what can happen then? The vapor can get heated up. Yes. Okay. So this would then create, heat up the vapor, and of course the temperature to which it actually gets heated would depend on the thermal mass of the vapor, but also it is placed on a chuck or something. So the whole thing will actually get heated up. Okay. The other thing is so the mask, whatever you are using, should withstand such temperature. So that is a very important consideration. And usually the photoresist undergoes chemical and physical changes at 120 degrees centigrade. So this is a disadvantage. Okay. If I want to now, so if the dose is very high, the temperature can actually go beyond this. Yeah. This is what I mentioned in a previous lecture. The photoresist may undergo changes during the ion implantation or exposure to plasma. So then it becomes difficult to remove the photoresist. Remember from the previous. So this is what I was actually